Now we want to spend a little bit of time talking about so a little more about electrolysis and specifically about the amounts of product you can get over certain amounts of time. So when you're looking at electrolysis, it's always a functional reaction, right? It is you causing chemistry to occur, you're applying current to make it happen. And so you generally want to kind of follow the progress of however much you're making over time. You're always doing electrolysis to create something, create product. And so how long is it going to be taking? And it's going to be based on the amount of current that you're applying. So ampere is the unit of current, capital A. It's oftentimes amp, is short. Ampere is a name of a scientist. And so amp is the usual shortening, capital A. And 1 amp of current is 1 coulomb per 1 second. 4 amps of current is 4 coulombs per 1 second. And so this tells you to relate coulomb, which is the amount of charge per time, right? How much charge is flowing into causing your reaction to occur. And coulombs is amount of charge that can be related to moles of electrons based on the Faraday's constant that we've seen previously, that capital F. So amps is coulombs per second, and then Faraday's constant gives you coulombs of charge per mole of electrons. So we can combine these to go from time, seconds, into moles of electrons, and moles of electrons, can get into chemistry amount of reactants products in our chemical reaction. So let's look at some applications or some of the actual mathematics here. So 1 amp of current, that would mean you have 1 coulomb of charge for every second. 1 coulomb per second is 1 amp. Faraday's relates moles of electrons to coulombs. So what we can do is literally combine those. So 1 amp is 1 coulomb per 1 second. Faraday's constant tells us that 1 mole of electrons for every 9.65 times 10 to the 4th coulombs. So, we would basically, what we do is we're canceling out the coulombs and we would get moles of electrons per second. That is an amount of reactant or product or something per second. That is a reaction rate right here. This explicitly right here, going back to our good kinetics, moles, is molarity, moles, whatever, per time. This is a reaction rate. So we can explicitly use these to get reaction rate information. And because you're using a constant current flow, you have basically constant reaction rate. And that would be a single term. But usually we keep the 2 terms up here, the amps and Faraday's constant. We don't write moles of electrons per second ever. And really it's because these amps, this math that we've done, this value that we got down here, this 1.04 times 10 to the -5, that is based on it being 1 amp of current. So normally you'd have whatever the amps for your particular electrolysis setup are, so it's going to be a different number. Usually it's a constant value, but it's going to be a different number, and we would need to account for that and how that's going to work basically. But so that's why you don't normally ever see moles of electrons per second as a value. You just have the amps and the Faraday's, but you can combine them to functionally obtain the actual conversion factor you want, this moles of electrons per second. Let's look at an example. How long would it take to produce 100 grams of aluminum from the electrolysis of molten aluminum oxide using a 5 amp source of current? All right, how long would it take to produce 100 grams of aluminum from the electrolysis of molten Al2O3 using a 15 amp source of current? So you guys want to start, what do we want? We are looking for how long would it take? So that means my answer is going to be time. Okay, so seconds, minutes, hours, some amount of time for this chemical reaction to occur, this chemical process. And so then the question would be like, what else do I have here that would let me kind of know what to do? So one of the things I want to key in on is, first off, that I'm dealing with electrolysis. So I know that I'm dealing with a driven chemical reaction, and the driving force is the 15 amps of power that are going into there. So when I see the 15, capital A is my amps. So if I have 15 amps, that means that there's 15 coulombs of charge per 1 second. So for every second, that's a time, we have 15 coulombs. So this current, this amps, is going to be the relationship between coulombs, amount of charge, amount of chemistry, versus time, that 1 second. Kind of looks like 15 down there, but that's one s, one little s. And so that's what we're dealing with there. So we know this is our kind of relationship factor between charge, amount of electrons, and time. So then the question is, well, what's the chemistry that we're doing? So if you remember electrolysis, that lysis is cutting apart these compounds. So Al2O3 to produce aluminum, right? We're trying to produce grams of aluminum. So if we're trying to come up with what is the chemical reaction, the product is going to be just pure aluminum. That is the goal, or the product that we are trying to get out of our chemical process. We're trying to make aluminum, produce it, it's a product. So then what would be the reactant? Well, the reactant is from this ionic compound, right? We're starting with the Al in the ionic compound. Aluminum is always 3+. So that means this process would be Al3+ to Al. So this would be the half reaction that produces aluminum. In order to figure out how charge is involved there, we need to balance it. The atom balance is already there, aluminum to aluminum. What is not there is a charge balance. I got 3+, and I got neutral. That means I need to have 3 electrons on the reactant side. So this is the reduction half reaction. We would be reducing the aluminum ions into pure elemental neutral aluminum species that we have right there. So 15 amps tells us the relationship between time and charge, coulombs. Our balanced half reaction tells us the relationship between charge, amount of electrons, and mass of aluminum. So this is kind of some stoichiometry. This is our particular kind of driving, or how quickly this reaction is going to proceed. So we can put all this together into one big old unit conversion problem, basically. So I start with my 100 grams of aluminum. And I know if I want to do some stoichiometry, if I want to relate it to the electrons, I need to turn it into moles. And so if I look up, the molar mass of aluminum is 26.98 grams of aluminum for every 1 mole of aluminum. From there, I can use that it is 3 moles of aluminum for every 1 mole of aluminum. I'm just pulling the coefficients off of my balanced reaction. So there's a 3 in front of electrons, there's a 1, implied 1, in front of aluminum. So that tells me that's my balanced chemical equation. Those are my coefficients. So basically for every, so for every 100 grams of aluminum, I turn that into moles. Now I have figured out how many moles of electrons have to go in there. So then the next thing I need to use is I need to go from moles of electrons to coulombs. This would be the number of charged particles. This is going to be in total charge that has moved. So 9.65 times 10 to the 4th coulombs for every 1 mole of electrons. This is Faraday's constant. This is just a constant value. This is what we've seen before, F. That's Faraday's constant, or F. Here we had the reaction coefficients. And here we had a molar mass, which I got off the periodic table or Google. And then finally, I want to go from, now I'm into coulombs. So basically, if I want to reduce 100 grams, if I want to gain 100 grams of aluminum by reducing the ions, convert to moles of aluminum, reaction coefficients, moles of electrons, Faraday's, this tells me the total amount of charge that would move in terms of how much I would move. And then so finally, I can use my current right there, that 15 coulombs goes by every 1 second. And that value we will label as the amps. Amperes, right? That capital A that we had right there. And so this would give us a time, if we just do the analysis, go all the way across, and the total amount of time is 71,534 seconds. So that is a totally acceptable time, but you're probably, that looks like it's a lot, right? But each second is very small, and we don't normally count seconds by the tens of thousands of seconds. So it's hard to tell. That's probably a lot of time, but just how long is it? So it's usually helpful to convert that time unit to something a little more manageable, a bigger time unit. And so what you functionally want to do, if you wanted a useful answer, that's an acceptable answer for the question. But if you want a useful answer, there are 60 seconds in 1 minute. There are 60 minutes in 1 hour, and you get 20 hours, 3,600 seconds in an hour. So how long would it take to produce 100 grams of aluminum out of molten aluminum oxide using a 15 amp source? 20 hours of time. So in short, a pretty long time, a pretty long amount of time to do that chemistry. And this overall process of working through these electrolysis, the time amount versus time of electrolysis, you're always going to be using, amps goes between basically charge and time. Faraday's constant goes from charge to moles of electrons. This is kind of similar to like the molar mass of electrons. It functions as a similar idea in the stoichiometry problem. Moles of your electrons versus whatever you're trying to work with. And then molar mass. It's also not infrequent that you need to do this other time conversion, because it is important to remember that this amps is coulombs per second. It's always coulombs per second. So if you're given like a time and you want to figure out mass, you would always need to convert to seconds first before you can do that. You can't just basically, you go from, you can't do coulombs per hour just out of amps. You would need something else. You need a different quantity of time and a different unit. But we can always figure it out. It takes a while to do this process to get 100 grams of aluminum with 15 amps of current. So I'll talk a little bit about this number. One thing is you'll see the 100 grams of aluminum, when I was writing the question, I just picked a random number. To give you some context, a roll of aluminum foil that like you'd buy at the grocery store is about 500 grams. So 100 grams of aluminum is not a ton of aluminum, especially in terms of if you're like a company trying to sell aluminum. That 15 amps, though, is not a random amp number, a random current number. That is similar to the current, or that's close to the current that your circuits are rated for in your house, like your plugs. It's not always current is dynamic, potential is constant out of there. So depending on the load that you're putting, the resistance, you're not always getting the same current. It's going to be dynamic. But you generally, 15 amps is like a reasonable kind of amount of current that like your functional devices, like if you're running like a blender or anything microwave, 15 amps is not unreasonable to be coming out of that. So one of the things you'll see is like if you're trying to make like aluminum as a company, it takes 20 hours to produce 100 grams, 15 amps ain't gonna cut it. And so that's why aluminum refineries have their own power plants. If you're trying to functionally perform electrolysis, you need a ton of current to do it. The big kind of culprit for aluminum is this 3 right here. You need 3 electrons for every 1 aluminum atom. So that's a really high cost. And so it's just really difficult to do that, or it has a really high cost. So you really need really high currents in order to get really a large amount of aluminum out, a functional amount of aluminum. So it really is difficult to do, and you need a lot of current. So that's why aluminum refineries have their own power plants. Participation 410, question 3. How many grams of bromine would be collected after 25 minutes of electrolysis of a molten sample of KBr using a 10 amp source of current? For reference, F is equal to 9.65 times 10 to the fourth coulombs per mole. This is the third question on participation 410, due Friday, April 10th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the document where these videos are posted. Again, how many grams of bromine would be collected after 25 minutes of electrolysis of a molten sample of potassium bromide using a 10 amp source of current? And Faraday's constant is given there for you to help answer the question. That is it for chapter 17. Lots of stuff in this one. It's kind of a big one. Kind of builds on itself, but also pretty jam-packed. Started with balancing, identifying redox, kind of just dealing with reactions, redox titration. I don't get one line here, but there's a lot to that. Everything with cells, everything with the cells and kind of building up electrochemical reactions, then a Nernst equation and electrolysis. Some of these more kind of applications, batteries, equilibrium, towards the end of the chapter here that we saw. Okay, 3 questions on participation 410, including one in this video. You want to find all 3 of those questions, get them answered, and get those answers submitted over on Blackboard by Friday night. Week 12 homework due over on Active on Saturday, post-lab for microvoltaic cells due Sunday, and then Friday also the lab technique presentation questionnaire. Not really great, just want to make sure you have a choice of what topic you're going to present about and what format, and importantly, if you want to give an on-campus presentation, when you want to do that. There's some times in that last lab, week of the last lab, so you can certainly do those. Or that week, the 22nd, second to last week. If you have any questions about anything, let me know. Otherwise, that's it for this week. There will be the answers to participation that go live Friday night. Otherwise, that is it for me. Next week, we got the test. If you want to meet to chat about the test, let me know. Otherwise, enjoy your weekend. I'll see you later. Bye-bye.